Hey Fahim, can you hear me?
Yes, sir. I can hear you, sir.
Okay, so the system is working, right?
Yes, sir. Yes, sir. Sir, we are waiting for a few minutes to join our chief guest,
Okay.
and then we can start. Our speaker
Okay,
is
that's
here also.
fine.
Our speaker is here, sir.
Fahim, is my sound clear?
Yes, clear.
Hello. Hello.
Assalamualaikum, sir.
Hello. Assalamualaikum. Hello.
Sir, thank you for joining. Sir, we can hear you, sir.
Hello.
Hello. So we can hear
Yeah.
you, sir.
Hello.
Assalamu alaikum, sir.
Sir, we can hear you,
Salam.
sir.
Okay.
The
Okay.
system is
Okay.
working.
Thank you. Okay.
Yes, sir.
Okay.
We are
The
going to
honorable
start, sir.
dean and
Sir, we are going to
participants and
start, sir.
speakers. Bam de jao. Ini siapa? Jawab.
Sir,
Okay. Okay.
sir, we are going to
So,
start, sir.
okay, please.
Assalamualaikum and very good evening to everyone. On behalf of IEEE Young Professionals Bangladesh and the IEEE Joshua University of Science and Technology student branch, it's my great pleasure to welcome you all to the IEEE Young Professional Bangladesh Talk Series 2025, held in collaboration with Joshua University of Science and Technology. I'm your host, Abdullah Sadek Fahim, chairperson of IEEE JAST student branch. Along with me, co-host M. Muhammad Ratul Hassan, graphic designer of IEEE JAST student branch. We are truly honored to be joined today by our respected chief guest, Professor Dr. Muhammad Abdul Mazid sir, Honorable Vice Chancellor of Joshua University of Science and Technology. Sir, your continued guidance and encouragement have always inspired us to push boundaries and aim higher. We are grateful for your presence today. It's also a privilege to welcome our distinguished speaker for the keynote session, Mr. Rony Alex Thomas, Associate Design Verification Engineer at Intel Corporation and Chair of IEEE Young Professionals Kerala Section. Also, we have session chair of this session, Muhammad Amjad Hussain Sir, Doctor Engineer, Counselor of IEEE Joshua University of Science and Technology Student Branch. Following the keynote, we will move on to a dynamic panel discussion on emerging research and innovation topics in the smart world, featuring esteemed panelist Dr. Muhammad Mihdi Hassan, Sir Assistant Professor, Department of Tripoli Just, and Dr. Farjana Khanum Ma'am, Assistant Professor, Department of Biomedical Engineering Just. She is also the advisor of IEEE Joshua University of Science and Technology Branch. This panel discussion will be happen after this speaker session. So before we begin, a gentle reminder to everyone, please stay with us until the end as well as we will have a nice session. Also, a feedback form will be provided in the chat list throughout the session. Please take a second to fill up the form to make sure you attendance. Ratul. Ratul, over to you now.
Assalamu alaikum. I'm Mohammed Ratul Hassan, currently serving as the graphic designer of IEEE
This meeting is being recorded.
IEEE student branch, and I'll be your co-host for the rest of the program. Now, I would like to introduce our speaker to you.
Okay.
জ্ঞান দেখে মোর কি ঠিক আছে নাকি কি করবো
Mr. Rony Alex Thomas is a system-on-chip design verification engineer at Intel Corporation, where since 2019 he has led end-to-end pre-silicon validation for server SoCs, from test planning to final sign-off across simulation and emulation platforms. An active IEEE volunteer, he is currently the chair of IEEE Kerala Young Professionals and serves on the IEEE Kerala section, with contribution across Region 10. He is passionate about semiconductor technology and career development. He speaks on industry trends, professional growth, and volunteering. Mr. Alex holds an M.Tech in Embedded Systems from Valour Institute of Technology, India, and enjoys programming in his spare time. Now, I would like to...
Ratul, wait, I think you can mute yourself. You have a sound problem. Okay. Okay, now we would like to invite our honorable chief guest, Dr. Muhammad M.D. Abdul Mazid sir, to provide his generous speech to us. Sir, please, can you please?
Thank you, host and co-host of today's IEEE webinar. And at the beginning, I'm grateful to invite me to this event. And in this event, there are many participants. Among them, our Honorable Dean of Faculty of Engineering and speaker, who is a specialist in this field, and other participants, faculty members, and my dear students. Assalamu alaikum. It's a very nice event that is organized by IEEE Just Chapter and other, related organizations of IEEE. I hope through this webinar, our students and faculty members, they can get the opportunity to learn and then interact with each other, and they can have idea of the topics which is presented by a very specialist keynote speaker. I hope such kind of webinar and other programs will be continued in association with the IEEE Just chapter and Bangladesh chapter, as well as international chapters. Hope with this event there will be a lot of opportunities to open for our students that will be very much beneficial for our future graduates. Done by this way. I wish a grand success of this today's event, and hope the discussion and lecture will be enjoyable to all of you. And thank you once again for inviting me. Since it's a very scientific topic and I am not relevant to this field, so I cannot say more related to this field. But I hope the event will be enjoyable to all of you. And thank you. Please pardon me if I just leave after this session. Thank you so much. Thanks once again.
Thank you so much, sir. Sir, we want to provide a small token of appreciation for your presence today. I want the Shweta Jaman to present the. I would like to invite our session chair, Professor Amdad Hussain sir, to provide this token of appreciation to our Honorable Vice Chancellor, sir, please.
Thank you very much. The president of IEEE is Just Student Branch. I am requesting the Honorable Vice Chancellor of Joshua University of Science and Technology, Professor Abdul Mazid sir, who always inspire our students for research, for innovation, for product design, as well as seminar and webinar. So I am requesting Professor Abdul Mazid sir to hand over this, to take this crest. Sir, please, to take the certificate. Sir, please.
Thank you so much. It's a great honor for me to have a certificate from IEEE just chapter, and I'm very much grateful. Thank you, session chair and other participants and faculty members and keynote speakers.
Thank you, sir.
Thank you so much, sir. Now, I would like to request our session chair, MD Amdul Hussain sir, to welcome and introduce our speaker and start this speaker session today. Sir, please.
Fahim? Fahim, can you hear me?
Sir, yes, sir, you are audible, sir.
Okay.
Sir, please welcome our speaker.
Okay. So the program IC Design from Concept to Product in association with the IEEE Young Professionals Bangladesh and IEEE Student Branch of JUST and IEEE. So in this program, we are welcoming Rony Alex Thomas, who is a design verification engineer at Intel Corporation. So I warmly welcome you to this event, and I'm very much happy to get you. As well as we are really proud that our Vice Chancellor, sir, who gives us time, and this event will more fantastic because Vice Chancellor sir already inspired us and deliver some speeches for the student to make some good things, make some good research, as well as to attend in the seminar and webinar, some things like that. Okay, and it's my great pleasure to welcome you to these sessions of the IEEE Young Professionals Bangladesh Talk Series, jointly organized by the IEEE Young Professionals Bangladesh and IEEE Justice Student Branch. Today's topics, IC Design from Concept to Product, comes at a time semiconductor industry is blooming globally. At the core of this revolution lies IC design, which plays a critical role in powering everything from AI to space technology. For our speakers are here today, these sessions present an opportunity with increasing global demand for skilled engineers in verification is a field where young professionals can truly make their mark. Our distinguished speakers bring first-hand experience from one of the most renowned semiconductor companies in the world, that is Intel Corporation. I visited there. It is really fantastic and wonderful for the electrical and computer as well as others engineers background student. I believe this insight into how to prepare for such a career, both technically and professionally, will be incredibly helpful for those aiming to enter this competitive industry. Whether it's about skill building, academic focus, or industry expectations, I hope all of you will actively listen and take notes. This could be a beginning of your own journey into the world of semiconductors. With that, I am pleased to hand over the session to the keynote speaker, as well as I am really thanks to the IEEE student branch as well as others IEEE to organize these events. Also thanks to the Honorable Vice Chancellor to give his valuable time for this program. Thank you very much. I am giving the floor, Mr. Thomas. The floor is yours. Please, please.
Yes, hello, am I audible?
Yes, sir, you are audible, sir.
Yes, thank you, sir. Thank you for the warm welcome, and thank you for the student branch, IEEE Joshua University student branch, and as well as IEEE Young Professionals Bangladesh for inviting me for this event. So I think I have a lot of material to cover, so let's quickly jump into the topic for today. And as sir just mentioned, I don't think I need to explain anything more about the importance of the semiconductor industry. Um, Before we go in, yes, Fahim, can you please enable present mode for me for the
You are already co-host. I think you can share your screen.
around PC one?
Okay. Okay, I'm taking care of this.
Yeah, just yeah. So as Sir was mentioning, this industry. It's gaining global traction, as all of you know, and it's a good skill to have. That is semiconductor industry knowledge. That's a pretty good skill to have for people from the electrical or electronics branch, or be it whatever branch that is. And so it's good that we discuss about topics like this. So the idea for today is I'm just going to take you through the steps, the flow, as we do in the industry, from a concept stage to a final product stage, where how we design an IC. Let me share my screen.
Okay, I think my
Yeah,
screen is
I
co-host.
have it now.
Thank you.
Yes, let me know when you can see.
Yeah, we can see the screen. Perfect and fine.
All right, good. Okay. Yes. So it's. I think you already got an introduction about me, more than enough information about me. So I work at Intel Corporation as a design verification engineer, and I'm also a very passionate IEEE volunteer for the last 11 plus years. I currently serve as the chair of Young Professionals IEEE Kerala section. I'm also part of the industry relations committee of IEEE R10, and I also serve in various other committees across IEEE. So that's just a bit about me. So let's dive into the topic. So before we start, I just want to give you a few heads up, right? So semiconductor industry, it's a very vast industry. So everything from simple LED to the most complex computer chips, those are all can be categorized as the semiconductor industry. So I'm not going into all of those things. And today's session, it's going to be focusing on the manufacturing, design and manufacturing of integrated circuits, or chips, as we call them commonly. And again, the focus is will be on a digital domain, because I'm from the digital domain, but digital analog all are interrelated. So yeah. And as I already mentioned, and as Sir also correctly mentioned, this is to set you on your own path of exploration. We cannot cover everything about this industry or this integrated circuits in such a short time. So I hope that this session will enable you, it will give you an overview so that you can do your own research and you can go down your own path of learning. That's what I intend to do. I'm not going to go into any big technical details or anything, but there will be some technical terms which you might not understand, some concept that you might not understand. That is okay. What I would suggest is you write it down. Whatever you don't understand, just write it down. I'll try to explain it as much as possible. And if you have any doubts, of course, I can explain it more for you. But still there would be some terminology, some cases which you might not understand properly. So my suggestion is note it down, and then later on you can do your own research. You have a lot of what do you say, sources available. You can Google it, you can ask ChatGPT. You have a lot of sources of information. So please make use of this session. So let's come to our topic for the day. It is about integrated circuits. It's the tiny chips, as we call them, that run the modern world. I'm pretty sure that all of you would have seen these types of chips. We have it in all shapes and sizes. There are different uses for it, etc. So don't want to go into too many details about these things. So here I've brought two chips from the two ends of a spectrum. On your left side, you see a very simple chip, a very simple analog voltage regulator chip, which has roughly 20 transistors, while on the right you have a Intel processor. It's an Intel CPU. It's an Intel server CPU. We call them as Xeons. So which has more than a billion transistors. So you have such a wide variety of chips available for different uses, for different applications, different shapes, different sizes. All these things are there. I don't want to get into too many details about that. You can just go and search. You will see lots of different types of chips. You can categorize them in different ways. One of the most simplest way you can classify them is based on the type. That is, we can classify them as pure analog, pure digital, or mixed. So most of our microcontrollers, microprocessors, etc., those are all mixed, where you have the main logic, the brain of that microcontroller is in digital, while its power supply, the memory, etc., those are in analog. Yeah, so that's just to give you an idea about it. Now, before we go into the process of building an IC, I just want to give you a quick idea about what an IC is, right? So when we say an integrated circuit, basically what we mean is it's an electrical circuit, and just like any other electrical circuit, it has uh, some very basic components like transistors, resistors, capacitors, diodes, etc. But when we say an integrated circuit, that we mean that this circuit, it is a very small size. It is in the order of nanometer level. So our transistors can be in the size of nanometers. We are talking about that scale of circuit. So that is basically what you can very simply say an integrated circuit is a electrical circuit which is shrunk down so that it fits on a small chip, on a small semiconductor material. So that's what an integrated circuit is. And if you're talking about an integrated circuit, let's start from the lower level of an integrated circuit. So at the lower level, as I mentioned, we have the basic circuit elements, and these circuit elements are that which is implemented on a semiconductor material. So you have transistors, we have resistors, we have capacitors, we have the interconnects between these devices. That is all implemented on a semiconductor material like silicon or germanium or something like that. It depends on the particular circuit. Now, when we connect these things together in a certain way, we get a circuit, right? That is the next layer of this abstraction. And when we have different circuits, we can have different types of circuits. So when we come to digital implementation, we have something called as gates or the gate level is what I'm saying. We have OR gates, AND gates, XOR gates, etc. Right? So these gates are again created using transistors, resistors, capacitors. When they are connected in a certain way, we get this gate level implementation. Now, these gates and other elements, other basic elements can be combined together to form a module. And different modules connected together will give us the final, what you say, the final chip, the final application type chip that we use. To give you a little bit more of an idea, let's look at it, right? So on the top here, I hope all of you can see this block diagram, this picture, right? This is a block diagram where you have a chip and various elements, various you can consider each of these these rectangular boxes as a particular module. So this you have this these are the input output modules. Then you have the ALU, which is the arithmetic logic unit. So if you see, these are the block level or module level implementation of a particular circuit. This is that of a simple microcontroller, right? You see, these are all different block level. Now, inside each of these blocks, you will have different circuits. So each of this block will be consisting of multiple circuits. So again, I've taken another example, which is a full ladder circuit. So those of you who have studied digital electronics will be familiar with what this is. So inside your ALU, you will have your full adder circuit. Now, how does a full adder circuit is made? It is made using these gates. So if you connect these gates like this, we have two XOR gates, we have two AND gates, and then there is an OR gate. So if you connect these gates in this format, you will get a full adder circuit. So you see, this is the module level abstraction. If we are talking about this abstraction layer, this is our entire integrated circuit. Inside that, we have a single module called the ALU. Inside that ALU, there will be a lot of different circuit elements, and out of that, one is this full adder circuit. And this full adder circuit, again, it is created using these different gates. And now, going one more level to the device level, we can see that an AND gate. You see this is an AND gate. An AND gate is created how? An AND gate is created using in its most simplest form. You have a power supply, you have a ground, you have two inputs, you have an output, and then what are the devices involved? You can see there is two transistors, you have three resistors. If they are connected in this fashion, in this circuit configuration, and you give power and you give ground to it, and then you give an input to two inputs and an output, you have the functionality of an AND gate, right? So this is how from a top level down, you can break down each and everything into a device level or into a transistor level implementation. Now, why I showed you this is because it is using this type of abstraction that we design circuits, we design integrated circuits. So I just wanted to give you an idea of how it is happening in the industry. So we cannot go and design everything at the transistor level. That is too complex, right? We cannot go, and if we have a billion transistor in an integrated circuit, we cannot go and design every circuit or every transistor one by one. That's not how the industry works, right? So that's why I showed you this abstraction layers. So just for your understanding, again, these are some of the examples. So we saw the voltage regulator IC in the beginning. I showed you the 7805 voltage regulator. This is the module level implementation. Again, another block diagram, just like we saw before. This is block diagram of a digital circuit, an ARM Cortex based microcontroller circuit. Again, this is the circuit level. This is the actual circuit level implementation of a 7805, where you can see different resistors are there. Then we have transistors, we have a diode here, etc. This is just for your understanding. And then if you actually look inside an actual 7805 IC, you will see something like this, where this is the actual representation. This is the actual semiconductor material on which the IC is built. So you can see different areas of this. When we see it directly, we might not understand what is what. But a certain area of this will be one transistor, a certain other area will be another transistor. This large area would be the input output area where heat dissipation is required, like that. So just to give you an idea, I just showed you. So now with that background, let's move into the design process of a generic IC, of a generic chip. How a chip is built from its concept stage to the final product stage. So before I move on, any doubts, anybody? If you have any doubts, you can ask directly, or you can even put it in the chat. All right, let's go. Okay, so I've broken down the design flow of an IC into these fundamental things. It's the creating an IC and manufacturing an IC. It is one of the most complex manufacturing and design process in the world right now. Because as I already mentioned, you're talking about nanometer level devices. So manufacturing this, it's a very complex process. But I've tried to break it down into its most fundamental things, right? So that you get an idea of what is happening. Each of these boxes can be further divided into a lot of smaller elements. In fact, we can have one session about each of these steps. right? We can talk hours about each of these different stages, but just for a beginning, for an initial discussion, I've just broken it down into these fundamental stages. Let's look at them one by one. And again, I'm telling you, if you have any doubt, please stop me. You can ask in between, or you can put it in the chat also. Or if you don't want to disturb the flow, then we can also have a question and answer session at the end. Just note down your questions, right? All right, let's go to the first stage, which is the device definition. So as you see here, this is the starting point of everything. This is where the concept of an IC comes to picture. So the what is happening here, right? Whenever we want to build an IC, there are a lot of things which we need to decide before we even start on the design process, right? So yeah, what happens in this device definition? One very important step is you should understand the market and the customer requirement, because any company, any industry who is designing an IC, they are not doing it for fun. They are doing it so that they can sell it and they can make a profit. So it is very important that they understand the market and market requirement, their customer requirements, right? They need to know that, okay, if I am going to create this IC, is anyone going to buy this IC, right? If nobody is there to buy that IC, then that whole effort is going in waste. A lot of money is going to in waste. So that is definitely required. Then once they understand that there is a market, then they need to define what is going to be the specs of an IC. They need to they can define an update to a product. So all of you would be aware of Intel chips, right? Intel i5, i7, those kind of desktop or laptop chips are there. You have different generations, right? So all the concept, when at the concept stage, Intel will go back and say, okay, am I going to release another generation of this chip, or am I going to go to something else, right? That kind of decision needs to happen. Now then, going further down, they need to define the functionality of an IC. What is going to be the main functionalities of this IC? Is this going to be a microcontroller, a microprocessor, a DSP, digital signal processor, a graphics processor, or anything, right? What is going to be the functionality? Then they need to divide the functionality by subblocks, just like we saw initially. I showed you our IC's functionality. It needs to be broken down into different blocks, different modules, like let's say cores, memory, then graphics cores, media engines, etc. There are a lot of different blocks out there, right? Then we need to provide the constraints of the IC. Constraints means what is the voltage this IC is going to work on, what is the frequency it's going to work on, what is the temperature range it can sustain, all these things. Also what is going to be the shape, the size, the package of this IC. All these kind of constraints, all these kind of things needs to be decided beforehand, before we even start defining the IC. And again, I'm not saying that all these things have to be set in stone. These things can alter as we go further in the design process of an IC. But for a starting point, you need to define these things. We need to have a starting point. Some tweaking here and there of that starting point, that is fine. But we need to define all these kind of definitions. Then one final thing that a company will be looking at is that they are going to look at, do we really have the feasibility to do this project? Do we have enough people? Do we have enough technical expertise? Do we have enough software, hardware capacity to create this product? So all these things, all these things have to be decided. A company's most senior people, they will come together. A product management team will come together. They have to decide on all these things before the actual design of a product can be initiated. So this is where a company decides. This is the stage where a company decides, am I going ahead with the design, or am I just scrapping the product altogether? right? So I hope all of you understood. So this is the device definition where basically the blueprint for our product is made, right? The plan, the master plan of our product is made, and based on that master plan, we are going to do the further step. Okay, moving on. Next will be the functional design. So if you take any IC, any chip, right? You have two different designs out there. You have a functional design and you have a physical design. The functional design is where you define the functionality, you define the logic in a IC, and that will be done as I showed you at the gate level or at the module level, right? That will be done, and the IC will basically be designed. Now, coming to the physical design part, I'll explain more when I get to that stage. But physical design is where you take this logic design or this functional design and you transform that into a transistor level design so that it can be sent for manufacturing. All right. So coming to a little bit more about this functional design, this is where the actual functional blocks of an IC is designed. And if you are talking about digital IC, then we design it using something called as EDA tools. Something called EDA stands for Electronic Design Automation. So if we are talking about, let's say, a microcontroller, you have a lot of sub blocks inside a microcontroller. So let's take that same ALU block that we were discussing, right? So the arithmetic logic unit. And inside that arithmetic logic unit, you will have adders, subtractors, you have logic functionalities, etc. So you need to go, a designer needs to go and design each of those blocks. And then all these blocks, all these different blocks needs to be interconnected together. That is what happens during this functional design. So to give you an example, so this is a simple design that I did using a specialized language called System Verilog. So this is one of the languages that we use in the industry. This is part of the EDA tools that we have. This particular set of languages, they are called as HDL languages, hardware descriptive level languages. So we have System Verilog, we have Verilog, we have VHDL, etc. So we use these kind of programming languages. These are similar to your other programming languages like C or a C++. But in this, basically you are defining the behavior, the logic inside your project, inside your product, right? So you are using a programming language to define the logic of your product. So this is a very simple counter, a very simple counter that I have designed, where you see you have these inputs, your outputs, then this part will be the actual logic where the counting happens, right? My counter is based on these two signals, right? This clock and reset. These two are my inputs, right? And my counter counts up based on these two signals. If reset is if my reset signal, it is high, then my counter will not count. Or if my clock is not there, my counter will not count. So this is a digital design basically. If these two things are there, if reset is not there and clock is available, then my counter will start counting, right? So you can see from the comments here. So this is a very simple way in which we define the behavior, the functionality of our IC. And as you can see, this looks somewhat like a C program or a C++ program. But the difference is that those C programs or C++, that will remain in software. But this program that I write, this will be converted into a hardware. Okay, I hope you guys are understanding. Now, that is what I have showed here in the bottom picture. If I were to convert this into a hardware level implementation, then I have in my EDA tool. In this is my EDA tool. This screenshot is from my EDA tool. When I do a compile in my EDA tool, I'll get something like this. Again, this is a block level representation. This is still not the actual IC. This is a block level representation of what will be implemented inside my IC. So this particular design, it will be converted into a hardware like this. So here you can see this round, this diagram represents a adder, which we already saw how an adder is. So these three will be my inputs. This count will be my output. So this block represents a D flip-flop. These are all basic elements in your digital circuits. You can go check them. So my design like this, which I write in the system Verilog, will be converted into a hardware level implementation like this. Again, still it's not in physical design. It is still not in a semiconductor chip or a semiconductor material. This is all still in a conceptual level stage. What my tool is telling me, it is telling me that if I write a program like this and if I compile it, if I synthesize it, then in my actual chip, a circuit like this will be implemented. Now, how all these needs to be converted into its basic circuit level, which we saw already, right? I showed you the adder circuit, how an adder is creating bits. So that level implementation that will happen in the physical design. So now, basically in the functional design stage, we are more interested in the functionality of the IC, in the logic of the IC. We are more interested in how our IC is going to, if I give a particular input to the IC, am I going to get the correct output, correct logical output? How it is going to be implemented on the actual semiconductor material, that is still that is later on. All right, so I hope you understood what is happening at a physical level circuit. Again, I already showed these picture. Once again for your understanding, as you can see here, this circle represents an adder circuit. Now, an adder circuit is created using these gates connected in this fashion. So here I have my adder. We can see the inputs, the outputs, and all these things here. Now, in place of this, I can put this circuit, right? I can put this circuit, this gate level implementation. But this again is not a physical circuit because there is no such thing as gates in the real world. Gates are again circuit abstractions that we create for our ease, for our understanding. If I want to actually get the functionality of an AND gate, I have to implement a circuit like this. I hope you guys can see my cursor and all, right? I'm pointing to different images. So finally, in place of this adder circuit, a gate level implementation like this will come. And then in the gate level implementation, when we go to physical design, an actual circuit like this will be implemented. A circuit like this. A circuit like this means we have 2 transistors and 3 resistors. So in my actual we will have to implement transistor 3 resistors and interconnect them in this fashion. We have to give the power, we have to give the ground here, we have to give the inputs here, we have to take the output from here. So we have to actually implement this circuit in our physical, in our semiconductor material. Only then will we get this design. I hope I made myself clear. Any doubts?
Thank you. No doubt, sir.
Okay. Yeah, let's quickly move on. So next, I'm going to talk about functionality. Again, we are in the functional domain only. We have still not gone into the physical part. Okay, so functional and design, as you can see, functional validation basically means we are going to test our design. we are going to test our design, and we have many different methods to do that. We have simulation, we have emulation, where we use FPGA based testing. Simulation will basically mean we are going to use a simulation software. We are going to feed this design. I showed you the design. Yeah, I can show you again. So you see this code that I have written. So I will feed that code along with some other code also, which is called a test bench, into a simulation software. We have different simulation softwares that we use in the industry. And what the simulation software does is it will go through this code. It will understand that, okay, this is the implementation and everything. And then it will help us to create a mathematical model of our design. And then based on that mathematical model, we can give it some inputs and outputs. I'm sorry, give it some inputs, and the simulation software will predict the output. It will give us the expected output from the design that we have given. And then we can look at our inputs and outputs, and we can see whether the design that we did is correct or not. Right. So this is again the test bench and design implementation for the design that I showed you before. So this again, I have written the test bench in the same system Verilog language. So what this test bench, this is the entire test bench. What this test bench does, it's going to give the inputs and it is going to it's going to monitor the output. So you see here, I have defined the inputs of my design. So this clock, reset, increment, these are all my design inputs, right? It was there in the design that I showed you before. Now I am going to put some values to this. I'm going to give a clock. Let's say I'm going to give a clock of 50 megahertz. And then I'm going to see how my design is going to behave. I'm going to give different values to reset. I'm going to give it 1, I'm going to give it 0, etc. And how my design is going to behave. So all these kind of things I can define in this test bench, and I can run a simulation. Along with this test bench, I can add my design also, and together as a package I can run my simulation, and I can look at the outputs. When I see the outputs, we can have outputs as text generated text, like text files, where we have a lot of prints which gives us the output, or even we have something like this called waveforms, where we can see the output inputs and outputs. You see this clock, reset, increment, those three are my inputs. Then I am looking at the output. So this output I am not doing. This output, it is calculated by the simulation software, and it is giving. So this is an ideal case scenario. This is where and how we can do it is because we know the actual how a product is supposed to, like if we have an AND gate, how it is supposed to behave. If I give 2 1s to the AND gate, then we know that the output also should be a 1. So we know
The recording has stopped.
we can predict the output of a device, output of these semiconductor devices, based on what input we are given. And that is what we are using here. That's why I said we use a mathematical model. And this simulation software takes care of all those things. So we can see these outputs like this, and we can see that, okay, it is working as expected. So you see here, when all the conditions are right, my output is starting from 0 to 1, then to 2, 3, etc. This is binary. That's why you see 1 1 0, etc. Right. So you can see the counting has happened. So you can see that, okay, my design is working somewhat correctly. Now again, functional validation, it's not just looking at it's not like a simple thing. We go through a lot of testing, a lot of different types of testing. We use a lot of different methodologies for testing. I don't have time to get into all of that, so I'm quickly going through. And as you can see, functional validation, basically it's like a loop with functional design. It's not a one-time thing. We have a functional design version 1.0. We do functional validation. We give feedback to the design team. They will come up with the version 2.0. Again, functional validation repeats. we give the feedback, they will come up with the design 3.0, and this continues. This continues until we have there is an agreement between the functional design and validation team that okay, now the design is in a good place, and then that functional design, that final functional design, will be going to physical design. Now, what is physical design? I think I have already touched upon it. Physical design is basically where you take your logic and you convert it into a transistor level circuit. So you go from a system Verilog code to actual transistor level circuit, and then one step further than that. Now, one step further is it's not enough to have a transistor level circuit design. We need to create create things called mask and other collaterals for manufacturing. Means we need to provide the foundry. The foundry is where manufacturing happens. We need to provide the necessary design elements which can be used by the foundry to actually create our circuit on a semiconductor material. So that it's a very complex process. So in physical design, you will basic idea is you create the physical layout. When I say physical layout, physical design is the stage where you decide where each transistor goes inside the IC. So if you have an IC of, let's say, 2 mm into 2 mm size, 2 mm into 2 mm square IC, right? Where each transistor in that IC goes, where each resistor in that IC goes, and how these things are interconnected together. That is basically what happens in physical design. But as I already mentioned, as the complexity of our chip increases, we cannot like do each transistor one by one. That's how they used to do it at the very beginning, right? They used to do like each transistor they used to design by hand in the very beginning of this VLSI era. But now we are not able to do that because when you're talking about billions of transistors, you cannot manually do that. So again, we have different EDA tools which take our code, the system Verilog code that I showed you. It takes that code and it compiles it into this physical layout. And it involves a lot of things like partitioning, floor planning, placement, routing, etc. These are all different stages in physical design. I don't have time to explain. Those who want to know more can go and understand more. You can search more. And also there is a verification in the physical design stage also, where after the physical design is done, there is a checking uh, to confirm that the design that we did, the physical design that we did, that is equivalent to the actual functional design that we have. And then there is always the design of mask and other collaterals for manufacturing. So this is where the physical design's output goes to the fab, goes to the manufacturing plant. And it is with this output, these mask and other design related details, that they create the actual circuit. And basically, that is what is happening in the next step. But before that, in physical design, so if you see, this is like a pictorial representation of a physical design. You can consider this as a full IC, and this is like a pictorial representation of how each thing will be in the IC. I just provided it here so that you get an understanding. See, you see, these red things are like transistors. This large thing, it's like a heat sink. These blue on the outer blue boxes, right? Those are the input output pins that we see coming out of the IC. Then all these blue lines inside, those are the interconnects. Those are the connections between various transistors and other components. This green things can be considered as resistors. This is just to give you an idea that inside an IC like this, if you take this entire thing in IC, here our transistor will be created. Here the next transistor will be created. Then these will be connected together like this. So it will be created in layers, right? That's I just wanted to show you a idea about that. And then this is what is called as a mask. And this mask is used in the manufacturing process. How that is done, you can see in the manufacturing process. right? So I hope physical design was clear. Next, we obviously go into manufacturing, and it involves basically taking our design, the transistor level design, and implementing that, creating that on a semiconductor material. The most common thing used is silicon. So you see, this integrated circuit IC manufacturing. It is manufacturing has a lot of stages, and where the actual transistors are created, it is created using one process called as photolithography. Lithography, that is the photolithography, basically means lithography with light. Basically, what happens here is you have the mask, and then you have a different wavelength print a particular pattern on a semiconductor material, and you can fill that pattern with something else like copper, or you can dope it to make it into a P region or an N region. It's a very complex process. I don't want to get into that at this point, but there are very good videos in YouTube available which explains each and every stage of this manufacturing very clearly, with good graphics and all. So you can go and look at it, those who are interested. So this lithography, you see the mask that I showed, that mask comes out of the physical design. And using that mask, a pattern is imprinted onto our semiconductor material, which is called as a wafer, right? And then this is again done multiple times. This is not like a one-off thing. This is done multiple times to create different layers, and finally you have outcomes something like this. So this is a wafer which has gone through photolithography. You can see different sizes of wafers. Each square in this is a separate chip. You will have to cut it up, and then you will have to package it to form the final IC. And this image, it shows you the different layers. This is like a representation of different layers of an IC. So you see at the bottom layer you have the transistor. So this is one transistor, this is another transistor, then there is insulation between them, etc. Then all these other layers are the interconnect layers. You can see this orange color, it's all copper. This is all the copper layers out there. This is different layers are there because we need a lot of interconnections between different transistors. That's how we implement our circuit. And finally, this big thing, it is the outward pins that we get in the IC, to show you that, right? So we have this our semiconductor material here, the one which is this one, right? This square, this chip is there. We call it a die before packaging. This stage is called as packaging. You take the die, and this die is basically it's very sensitive. Like one speck of dust can disturb the whole die. So we need to cover it in some protective material. For simple chips like this, it can be some plastic kind of things. For bigger chips, you will have more exotic materials, etc. So that again depends on the type of chip and the use of that chip. Those chips which are used in space, things will have a different type of packaging. Those which are used in let's say automobiles or industrial grade chips will have different packaging than what we use in our simple mobile phones or our computers, right? So that this stage is basically called as packaging. So we have the transistors implemented on our not just transistors, all the circuit elements implemented on our semiconductor material. Then we have to cut that semiconductor die, as we call it, that small square. We have to cut it up. Then we need to do packaging. We need to protect it. And then we also have to bring out the inputs and outputs, right? Input output pins, we have to give connections like this, so that we can put it in a circuit board like this and use our IC. So that is basically what all happens during manufacturing. I know I just zipped past that, but time is not allowing me to explain more. But those who are interested, you can go and search for the manufacturing process of an IC, or you can search for photolithography, where you will get really good explanations. Coming to, I'll quickly wind up. My time is done, but I need like 5 minutes more to just quickly wind up. Again, once the IC is manufactured, you will have something called as post silicon validation, where you actually take the IC, the manufactured IC, and do validation. So this is an example. You can see we have this IC which is under here. This is a fan. You can place the IC in a board like this. This is called as a test board. So here you have a slot for an IC, or here you might have a slot for an IC. I don't know. I just took this picture, right? So you have a board, you have a testing board where you put the actual IC, and then you can again do a lot of testing. You give inputs to it, and you see the outputs, whether everything is working or not. And again, just like functional validation, post silicon validation also goes back to functional design. And why is that? Because usually what companies does is that they don't just simply manufacture an IC right away and then send it for what you say, send it for to the customers. What they'll do is they'll do like a small batch of test chips. They'll do a small batch of test chips, which they will use for this post silicon validation. And only if post silicon validation is satisfactory, they will go for mass manufacturing and they'll send it out for their customers. If post silicon has some issue, some major issue, some big issue which you cannot solve by any software updates or any kind of tweaking, then you will have to go back to functional design. You have to uh, rectify that error, rectify that bug. Then you will have to go through physical design, functional validation. All these things have to happen again, and then only you will go for mass manufacturing. So if you see, there are different stages of validation in the design flow of an IC, which means there are different layers of testing. And why these layers of testing are there? It is because manufacturing an IC is a very cash intensive. It's a very expensive process. If you can find some bugs at the functional validation itself, you are saving a lot of money for the company. So if a IC is manufactured, if it goes out to the customer and then you find an issue, then you have to recall that entire IC, and it's going to be a huge loss for the company if they have to remanufacture it, redo the design, and then manufacture again, right? So that's why all companies have a lot of validation going on. And in fact, if you look at the semiconductor industry, you have more number of validators, you have more number of people working in testing, different levels of testing than designers. So this is again one very good job opportunity. A scope of job is more in this validation domain, verification, validation. There are different types of testing available there. So yeah, that I just wanted to just mention that. So that is all about the hardware part of it. And along with that, I've just mentioned two more things. I'll quickly go through that, which is called as a firmware design and validation. So firmware is basically a code, a companion code for your IC. It is not there for all ICs. It is usually there for the more complex ICs where you have multiple inputs and outputs and different types of communication protocols available. So things like you would have heard about these things, right? BIOS or embedded OS or maybe an RTOS or things like that. So these are what we call as firmware. This is not the typical software that you see that you run on your Windows or your phone. This is the actual code, the software code which resides inside your IC. These come sometimes pre-packaged with your IC. It is there in non-volatile memories inside your IC. This is like very small pieces of code. And what happens is this code is responsible, this firmware is responsible to bring your IC up. When you give power to your IC, this firmware, for example, if you take care of a microcontroller or a microprocessor or even a graphics processor, When you apply power to this processor, it is your firmware which comes alive and it takes care of the initial bring up of your IC. And then this firmware, once it does all the basic configurations and bring up, it will hand over the control to your operating system, right? So that firmware design and validation also, it is a very important step in the design process of an IC. That's why I have mentioned here. And this is also, again, usually done, this a semiconductor company who manufactures a product like a microprocessor, they will have their own firmware teams there, which designs the firmware for that particular product. Yeah, so that is again one of the steps which happens in the design flow of an IC. So this, I hope, gives you a idea about how an IC, a generic IC, is designed from its concept stage, from its device definition, all the way to manufacturing, and also the various other components which is there along with this IC, like the firmware. So this is basically the design flow. I just want to quickly give you two more slides and I'll be done. So it's about anybody who's interested in starting a career. So these are the different options that you have out of this placements, direct interviews and referrals. All of you guys know. One other thing is that internships. You can try for internships in many different semiconductor companies. Many of them provide, so you can try for internships. You can, of course, go for post-graduation in VLSI design or embedded systems or something like that related to this. And of course, you have specialization courses where you are taught like one particular domain. Like you want to study digital design, they will teach you digital design. These are supposed to be small scale courses. Yeah. Now, one final piece of advice as someone from the industry, and if anybody looking to get into this industry, I would say is that this is a very technical intensive industry. So you have to be really strong in your fundamentals. That is your digital design, your analog electronics, digital electronics, all those fundamentals related to VLSI, fundamental related to semiconductor industry. You have to be strong in that. And nowadays you have a lot of opportunities to gain practical knowledge where you can go and you can learn these design and you can do on your own. You can do some design and you can try running a simulation. You have online tools for that, right? You have a website called EDA Playground where you can go and you can code something up in system verilog or verilog and you can run some simulations. So try to gain that practical knowledge rather than just theoretical knowledge. And then it is good to always understand the industry demands. Right now industry is all about AI and all people are going after AI chips, and also understanding the different trends in the industry and uh, improving your skills, improving your knowledge based on that. That is really important. For that, what you can do is you can network with various professionals and people who know more about this industry, and also the recruiters, the job recruiters in this industry. And one other thing which would help you is you can go and look at the job posting by these companies, right? You can go to a page of any company and you can look at the jobs available and what are the skills that they are looking. Some companies will very specifically say, we need expertise in this tool, we need expertise in this domain, etc. So that will give you an idea about what should be your what tool you should learn, or what is the skill that you should be acquiring. So that will be helpful. So yes, I know I've gone past our time a little bit, but we can spare a few minutes for questions.
Thank you to our speaker. Now I'd like to start the question and answer session. You can ask directly through the microphone or you can ask through the chat as well. Now I want to start by myself. My question is that Intel is one of the companies that a lot of people are interested to work at. So apart from the technical things, what was your experience on a personal level? Like how was the community? things that you liked and things that you did not, etc.
Okay. Yeah. So this is very personal to me. Like what I'm saying, that's my own personal experience. So I don't know how your experience is going to be. So I joined in a team which was very supportive. I joined as an intern. I was doing my master's there and I joined as an intern, and they were very welcoming. Even though I was an intern, they considered me as part of that team. So it basically your experience will depend on the team that you are getting into. I know several people in my classmates who have joined same company, different teams, who have had bad experience. So it basically depends on which team that you are going getting into. But generally speaking, the work environment and everything in Intel is good. It's a great place to work at. I'm talking about the employees, the interactions, etc. Technically speaking, again, depends on what kind of product that you're working on, how much work that you're going to get, how good learnings, whether you are going to get good learnings or not. Those again will depend on what type of work that you are into, your team is into. But generally, I see that it's a good place to work at, in my personal experience. But right now, Intel is facing some issues in sense of Intel's products are not, we are facing financial issues and all. So right now, there are some difficulties related to that. But in general, I would say it's a good place to work.
Thank you, sir. I have a question. Actually, I don't know, it's coincidentally, we had a BLSI exam today, and we have understood almost all the topics you have mentioned on your presentations. So my
Oh,
question is very direct, and it is that as a fourth year or undergraduate students in Bangladesh, what will be our roadmap to get into Intel from Bangladesh directly, and what could be a impactful research topic right in the 2025, which can be impactful for your company and can be a good journal, at least you can say.
okay. So, uh, okay. So I'll tackle the first question. So first question, you have talked about getting into Intel, right? So you are talking about Intel or any other semiconductor product company, right? So I have to be honest, I don't know about the situation in Bangladesh. Any companies are there or not? I'm not aware of it. But if you want to join Intel,
Yeah.
yeah.
Um, we have Ulkasemi in Bangladesh, which is working as a semiconductor, the biggest semiconductor company in Bangladesh, who provide IC design system, and but not they are not doing fabrication right now, but they provide the design. We
Okay,
had an
so
intern
they
over
are
there for
they are a
5 days.
service they are a service based company, is it?
Yes, yes.
Okay, right, right. Yeah. So see, be it Intel or any kind of company like that. So if you want to get into it, as I mentioned already, right, it's you need to be good with the fundamental things. This is a very technically intensive job, right? This is like it's not enough that you know some basic stuff and you are good. No, that's not how this works. So you have to know the fundamentals of all these digital electronics and log electronics, those kind of things to get it, right? Once you get in, you have to based on what role that you are in. So the skill set of a physical design engineer is completely different to that of a functional design engineer, right? The logic, like we can it can be called different names in different companies, but physical design, functional design, they are like two opposite things. Physical designers are more interested in doing the routings and looking at design rule violations, how a transistor affects the heat dissipation of that. They are more interested in the physical aspects of the transistor, you know. But a functional design engineer, he is not at all if I'm talking from a digital point of view, if I am a digital logic design engineer, I'm not at all focusing on transistor. I don't care about the transistor. I just care about how my logic works, how good I write logic, how efficiently I can write logic. That's what I am concerned about, right? So what exact skills you need to acquire depends on which part of the industry or which flow of this industry you get into. But for everyone, fundamentals are important. So to get in, you have to have good fundamentals. And as I already mentioned, try to do some small level projects, right? Small level projects you can try and do to get some hands-on idea. So we have initiatives like Tiny Tape Out or things like that, where you can even submit your own designs so that it will be manufactured and you will get an actual chip. So there are initiatives like that going around. There are a lot of STEM chip things like that. So you can, if you want, you can go into that level also. But as a as a student, I won't say you go to that kind of level, but at least you should get that basic idea of how to design a small chip, right? How to design a small chip and how you are going to test that chip. You write a test bench, you do some simulation, and if you have the facility of FPGA boards in your college, you can even load your design into that FPGA board and you can actually see whether it is working properly or not. So those kind of basic things, fundamental things, if you get it right, I think you that is the most important part, I would say, the fundamentals, and also gaining this some little bit of practical experience. You can go to your professors, who are interested in this VLSI domain. You can go to your professors or people who are doing research, and you can assist with them. You can learn with them. But thing is, these are all extra to your curriculum. Your curriculum will teach you the basics. Okay, your VLSI or digital logic or subjects like that will give you the basics. But go and do something with it. Practically apply it, and learn from that. That, I would say, would be the most important skills to have. What was the second question? Second part of that
Yeah,
question?
I think the second question was what can be the research topic which can be a good journal in this field right now, if you consider any observation, your observation.
So one thing, this again depends on what actual domain that you are interested in. See, if you are interested in digital design, you have a lot of topics there, like you know, AI. AI is one hot topic now. How you can create designs for AI, how you can optimize designs for AI. That is one thing. Uh, or other thing would be something which was coming up recently in the past years is what is called as a risk V architecture, which is an open source architecture, right? You have Intel architecture or the x86 architecture and ARM architecture, which are like proprietary architectures, which is most commonly used. But then you have risk V or risk 5 architecture, which is open source. So your entire architecture is open source. You can take that architecture and you can do anything with it. So you have risk 5 based CPUs, GPUs, different types of processors, computers, etc., right? So that can be one of the things. RISC-V based AI acceleration, that is something which is going on right now. So these are some of the things which you can try if you're interested in the design part. If you're interested in the validation verification part, again, many of the upcoming things still is related to AI, how AI can be used for better writing better test bench, how AI can be used for testing more effectively. Those kind of things are there. Then if you're going into physical design, unfortunately, I'm not an expert in physical design because that's not my area. Physical design, you would have to check with somebody else. So what I would say is you can go into any of the reputed conferences or publications, journals, right? You can go and search for any of those. Like IEEE itself has a lot of journals and conferences related to semiconductor. You can go to IEEE SSCS or CAS, SSCS Solid State Circuits, or CAS Circuits and Systems Society. So they have a lot of premier conferences. You can go and check for what are the topics, what are the recent trends, what are the recent papers going on. Yeah, you can check for that.
Thank you. Sorry, I got disconnected for connection problems.
No,
Thank you to the speaker for his
I
insightful.
think 1 second. I think we have few questions in the chat. Let me see. Okay, we
Actually,
have. Yeah, are we out of
we
time?
have, yes, we are in short of time actually.
Okay, sure. Yeah. So what I would say. Okay, just 1 second. Yeah.
Mhm.
Once again, I would like to conclude. If you have more questions, you can connect me over mail or LinkedIn, and if you want have more questions, I can answer it there. Once again, I would like to thank the IEEE Young Professionals Bangladesh section, and also I would like to thank Jashore University Student Branch for inviting me and giving me this opportunity. I hope this was useful for all of you. Thank you very much.
We are also thankful that we got you as the speaker. Now, I would like to invite Mohammad Amjad Hossain, Doctor Engineer, Counselor, IEEE Just Student Branch, to present the certificate of appreciation to the speaker. Sir, are you
So
there?
Rizwan, please show the certificate.
Fahim, you can also share that if Shohiduzzaman device has some problem. Okay. Okay, that's great. Thank you, Thomas. Thank you very much for your wonderful presentations. We are really happy, and I think our students will learn something. And again, a big hand for you. So, on behalf of the IEEE student branch, please take this certificate, please, and big hand for Thomas, everybody.
Thank you, sir. Thank you very much.
Thank you very much. Please, Fahim, please.
Okay,
Thank
sir.
you, sir. Thank you, sir. Now, I would like to invite Suhail Rana, Chair IEEE Young Professionals Bangladesh, to present our certificate of appreciation to the session chair, Mohammad Amjad Hossain, Doctor Engineer, Counselor, IEEE Just Student Branch.
Okay, I think Surana sir is not there. I would like to request Dr. Aminul sir to present the certificate to our counselor sir. Aminul sir, please. Can you please unmute?
Thank you. Thank you. Soelrana is busy for an important task. That's why I am here to kindly request Professor Amjad sir to receive this certificate of appreciation on behalf of IEEE Young Professionals Bangladesh. Sir, if you kindly receive the certificate.
Thank you very much, sir. Thank you.
And thank you. And I express my sincere thanks to the speaker because today we had a very good engaging event, and I think the students are very much eager to listen to the speaker. So thank you, sir, for your nice presentation and your uh, or motivating our students to work in this field. So thank you, Mr. Rony Alex Thomas, YP Chair of Kerala section, and thank you to Just Student Branch for organizing or arranging the event in a well-organized manner. Thank you all, sir. Over to the host.
Thank you, sir.
Thank
Sir,
you.
we can.
Now, I would like to proceed to our second part of the program, which is the panel discussion. We have two panelists, Dr. Mohammad Mehdi Hassan, Assistant Professor, Department of Electrical and Electronic Engineering, Joshua University of Science and Technology, and Dr. Farzana Khanum, Assistant Professor, Department of Biomedical Engineering, Joshua University of Science and Technology. And we have the moderator, Dr. Muhammad Aminul Islam, Associate Professor, Department of Electrical, Electronic and Communication Engineering, Military Institute of Science and Technology, Vice Chair Technical, IEEE Young Professionals, Bangladesh. Now, I'd like to hand over the microphone to the moderator. Thank you.
Thank you. We already had the technical talk from our technical speaker, Rony Alex Thomas. Now we are moving to the second part, which is a panel discussion from the young professionals. They will share their experience, their journey, their guidance for our graduating students and young professionals so that they get motivation for pursuing their higher study, their research, their target job market, and they can listen from the young professionals. We used to listen from seniors, but this idea is given by Professor Selam Madam so that we can hear from the young professionals and get the recent guidance, get the motivation from our young professionals. So we are happy to have two young faculty members from JUST, Dr. Mohammad Mehdi Hassan from Department of IEEE as the first panelist, and the second panelist is excuse me. Our second panelist is Dr. Farzana Khanum, Assistant Professor, Department of Biomedical Engineering, and she is also working as the advisor of IEEE JUST student branch. So we'd like to start with Dr. Mohammad Mehdi Hassan, and I will be actually doing some question and answer so that we can get to know the speakers. They will share their experience, their educational background, and others. So first, going to start with Dr. Mohammad Mehdi Hassan. So would you please share your educational experience and please introduce yourself so our students or our audience get to know your current affiliation and background. Dr. Mehdi.
Thank you, Dr. Muhammad Aminul Islam, sir. And my gratitude also goes to IEEE Young Professionals Bangladesh and IEEE Joshua University of Science and Technology Student Branch for arranging this wonderful session. As you know, my name is MD Mehdi Hassan. I graduated from Bangladesh University of Engineering and Technology, and then I had the opportunity to complete my PhD from Australia, Deccan University. My research topic goes around uncertainty quantification in deep learning methods. During my PhD journey, I took part in many industry and academia collaboration projects. And also I had the opportunity to attend IEEE summer school at Swinburne University, Melbourne. And during my PhD journey, I have also had the opportunity to meet some wonderful persons who had very rich research profiles in deep learning areas. And yeah, that's it. Thank you.
Thank you, Mehdi. I also followed the similar background. I also graduated from BUET, then completed my PhD from Australia. So hearing a new PhD holder from Australia, because I completed 10 years back. So the experience from Mehdi will be recent experience, and the guidance for higher study or recent research topic will be updated on for our current graduates. So we will move to the next panelist. So we also have Dr. Excuse me. We also have Dr. Farzana Khanum. So she is from a biomedical engineering department. So would you please share your educational background and introduce yourself?
Thank you, sir. Can you hear me?
Yes.
Okay. Thank you, sir. And thank you, IEEE Justice Student Branch, for organizing such a wonderful event in a short time. And they arranged the event in a very organized way. And first of this event, I like to show the gratitude to the IEEE young professionals, and also in few times ago, we all learned a lot of things about IC design to concept to the towards the products and the manufacturing processes of different types of ICs. And I think it will really help us to learn about really insightful thoughts to our students, and as well as our all the participants. And my educational background is I completed my BSc engineering degree from Tripoli department from Kuwait, and then I completed my MSc and PhD degree from Kuwait biomedical engineering department, and I have joined in just since 2017 and working as an assistant professor in biomedical department. In my my educational features and research field is basically functional neuroimaging field, and it's the field of our cognitive activity is against our different of working activity, how our brain works against our functional activities. Basically, my research field is about. And thank you. And if you want, I can show some research related works of mine. Thank you.
Thank you, madam. So our we'll be getting about the research topic further later on. So we'll be moving to the next question. Like one of you is doing research in machine learning, and other one is doing research in biomedical engineering. So my question to Dr. Mehdi, that what motivated you to do the research topic on machine learning? And second question will be, what motivated you to pursue your PhD in Australia?
Thank you, sir. This is actually very basic questions and very core questions to my journey. So I actually graduated in electrical and electronic engineering from BUET, but after completing my graduation, I understood that the topic that I have done the undergraduate research, I mean the thesis, it was on electronics. And I understood that I don't feel so much enthusiasm in electronics. And then after I joined Joshua University, I thought for some period that what should be my research direction? What should be my research goal from now on? As I have joined as a university teacher, lecturer, I need to do research. I need to complete my PhD. I need to guide my students towards their better future, which obviously includes guiding them towards research. So after some thought, I figured out, and also from my undergraduate, I figured out that coding, programming attracts me much. I love programming. And then after joining Just, I did some research with one of my university friends using very basic machine learning on power sector datasets, basically the load forecasting and NILM, non-intrusive load monitoring. And we got some paper published. I mean, just the two of us, we tried for, I think it was between 1.5 years and 2 years, and we got published 2-3 good papers. And after that, I thought, okay, So the thing that we have done on those papers, it was just using basic Python modules that's already available there, and just load the data, some pre-process them, and then feed them to the module and just do the prediction or classification or whatever, the forecasting. And then I thought that, okay, here I don't see much contribution from my side. I'm just using my the already available Python modules for the classification or the forecasting or whatever. So then I thought that if I want to go deeper into it, then what should I do? And during that time, I figured out that if I focus on classical machine learning, I need to do need to go very deeper into the core mathematics, core statistics, and that would be a bit tough for me. Then what can be done? Then I also figured out that, okay, instead of core machine learning, classical machine learning, what can I do that I can move towards the deep learning, which is not so much. I mean, at that time, it was 2017. At that time, it was not too much mathematical based. At that time, it was like implementing an idea, coding it, and then getting the results and trying to describing the results, what is going on behind. So I thought it could be a good research direction for me to do the research and also contribute inside the module, not just using the already available module. And from this thinking, I moved towards the deep learning arena. And regarding the second question, the Australia, my first priority was the environment. I mean, I have heard about a lot of my friends and my senior brothers and sisters that many of them get homesickness after they go abroad, and majority of the part is due to the very drastic weather change compared to Bangladesh, and also obviously they're far away from their relatives and other things. So what I first focused that I cannot bring my whole relatives to the abroad, but what can I do? I can choose the place which could be similar to in environment, in respect to the environment, similar to my country, so that I don't feel too much bad. And so my option was Canada, USA, and Australia. And among Australia, I figured out that Melbourne is not too much. It's not too much hot, too much cold, not too much cold. It's in between 5 to 20 all the year round. Sometimes it goes below that or above that, but it's endurable for me. So I thought, okay, it could be a good opportunity for me. And during that time, I got I noticed an message in Facebook, in a Facebook group, in our university Facebook group, saying that in Australia, Deakin University, at a specific institution named ISRI, they are looking for PhD students, and the field would be deep learning, uncertainty quantification, or trust-related quantification in deep learning, vision-based deep learning. So I just grabbed the opportunity, and the good part was I just sent them my CV. They directly sent me the offer letter. I didn't have to go through any screening process. So that's why I didn't think about anything. I thought that it's a gift from Allah Ta'ala that He gave me this without any going through any hassle. So I didn't thought anything else. I just took the opportunity and went there. Thank you, sir.
Thank you very much. I think you have shared your experience, but there are several points for the students to take from here. So I think lots of students are doing research in machine learning, and as you said, they are just applying their code or already available models to some data sets. So I think as you shared that we need to add some values there. So we need to actually add some values there and to do some research. So that is what you added. That some read the favor from the lot, like we got the circular from Facebook or our friends that there is a vacancy from this university or that university. So I also some luck like you, because when I was doing a job back in 2009, so then I also got a similar type of information that one of my friend's professor gets some funding from Australian Research Council, and he is looking for students. So I contacted directly. At the time I had my IELTS score, so I applied there, and they took some interview, and then I got the admission. So I hope this is sharing some guidance for the current students that how the application process, if the professor have some funding, they can take us anytime based on the funding. And the application process or the selection process is something sometimes like that, not always. And if the professor doesn't have his own funding, then you have to apply through the central university funding or central application, and you have to go through some competition there. So the situation at some part is still similar to 10 years back what I faced. So that's why I'm feeling a bit nostalgic that I also did the same way or applied in the same way. So
So
now I
hearing
like to
hearing from you, I feel the urge to meet you personally. I mean, you have the similar experience, almost similar
yes.
to me.
Yes,
And
yes.
also I want to
I
add
was before the event. I was just looking at your profile that yeah, you just submitted your PhD thesis. It is updated like that. So immediately after your undergrad, you did the PhD directly, I believe.
yes,
So
sir.
so I also did the same. So students, those who are in the fourth year, you might plan or you might plan like this, that you might finish your study first, then you might do industry job or academia job, whatever you wish. You might do after finishing your masters or PhD, because when you are in a flow like studying, so I believe continuation of the study and completing the degree might be helpful instead of giving a break for 5 to 10 years in some industry job.
Sir, here
So
I
inshallah,
want to add some points if you allow.
yes, yes, go ahead.
Uh, First is during my time, what I noticed that there might be some cases that professors handles fund in Australia, but most of the cases now the fund goes through centrally through the university admission, overseas admission process. But still, the thing is, though the university provide the funds for the students, you have to apply through the university. You can't directly apply to the professor like some of the universities in USA. You have to go through the university. What it does, the university sends it to the respective departments, and the departments ask its professors if anybody is willing to supervise these students. So what you can do, you can check for or look for professors in any respective departments. You can talk with him or her, and if he or she agrees, then you can go through the application process. What it does, it will accelerate the process, because whenever it goes, that your application will go through the departments, that professor that you have already contacted will directly say that, okay, I know these students, I want to supervise him or her, so okay, allow it. So that's the thing, but still you have to go through the central admission process most of the cases in Australia. And the other thing is, from my side, what I can say, my supervisor during my PhD and even after my PhD, my supervisor, my co-supervisor always asked me if you know any students who is very much interested in deep learning, in vision-based deep learning, in LLM-based deep learning, and another aspect. I mean, the core thing is deep learning, and you have to be enthusiastic enough to contribute inside the models, inside the architecture. So they always ask me if I know somebody so that I can send them to them, and also I can arrange meetings and collaboration teams with them. They always encourage me. So if students find they're interested in deep learning, they want to contribute in these fields, they can come and contact me. I will try to connect them to my professors, to my co-supervisors from Australia. Thank you, sir.
Thank you, thank you. I think students will be motivated, and as you shared, definitely we have to apply through the university central application process. Then the applications are shared with the professors, and then the professors can select you. And recently we had a lecture from an Australian professor a few days back. I think if those who have joined, they already know they are evaluating each application based on 5 criteria, like your BSc university and CGPA, MSc university CGPA, then your publications and research experience, uh, uh, your IELTS score, and your SOP or some experience, a job experience or something like this. So I believe you should develop your develop in each part of the um, evaluation criteria so that you can compete with all the applicants. Like what I have seen that in central funding, students from Malaysia or Korea, they are getting some priority. They are doing their BSc in Bangladesh, then MSc in Malaysia or Korea, then PhD in Australia, something like that. Because when you do MSc, even MSc in Bangladesh and having some publications, that will give more weightage to your application, and that will help you to get selected in better, good universities with good funding. So I think after BSc, you might apply directly, as well as you might think of completing your MSc with good publications from home and abroad as well. Like you might uh, uh, do your masters from Bangladesh or from any other country with some good publications that will help you to get admission in good universities in Australia.
So
So
in my
now,
case,
yes,
sorry, sir, sorry to interrupt you.
yes, yes,
In
yes.
my case, after I got admitted there, I just looked for why I got admitted without getting through any screening process. So what I have found out that they were very interested in my papers, that I already published good quality articles. That's why they didn't bother me regarding any interview or anything. They just directly send me the offer letters. So the articles, good quality articles, is a very big point here.
Thank you. So we should. So as I said, so your research experience is a is will continue a good weightage. So in your BSc level, from the very beginning, if you focus on doing research and make some good publication, definitely that will give you a very good dividend for getting admission in a higher rank universities. So now we are going to move to Dr. Farzana. So would you please share your experience in doing your PhD in Kuwait? So what motivated you to move to biomedical engineering from Tripoli, and what are the advantages, or uh, what was your motivation to do your PhD in Kuwait?
Okay, thank you, sir. Uh, Actually, my journey is quite different from yours and Dr. Mehdi, because I have accomplished my PhD and MSc in Bangladesh, Kuwait. Um, at first, I like to tell you about my BSc journey. I completed my BSc in 2012, and my BSc thesis was about antenna design. And then I got a job in private university at Dhaka. And after 2 years, I think that I should complete my MSc also. And then at that time, I returned Kuwait and wanted to complete my MSc in Tripoli. But at that time, in biomedical, they launched the professors of some professors of Tripoli launched biomedical engineering department, and they also opened a lab, biomedical signal processing lab. And in that lab, I some in some few days I went there, and I really feel very I feel very amazed to see their working process of different type of signal. They used and they launched some signal processing devices like EEG, EMG, ECG signal processing device to acquisite the data from the, and this process really feel me very creative and curious and about their works. And I learned some of their data acquisition process from their professor Dr. Mohidin Ahmed, and that activity really helped me to convert my MSc journey from Tripoli to biomedical engineering. And their lab process and lab days was very learning, very much helpful for my journey to biomedical engineering. And then I convert my MSc journey from Tripoli to BMA, and then I have done my research on EMG, that means muscles activity, muscles activity to signal processing, and from that day. And then after 2 years, when I got my MSc degree, then I thought that I should PhD on that process. But I didn't think that EMG signal processing is very much tough to, because there are lots of works are have been done on that in the research fraternity. So I think that the EEG, that means brain signal, is very much popular and famous for publishing the works. And so I converted the signals processing journey from EMG to EEG, that means brain signals. Basically, brain signals is very much in these days, brain signals activity or processing works or publishing journey is very much popular in this modern world. And today's our world, excessive multitasking, that means social networking sites at a time, we are using Facebooks, or we are using Twitter or X, and really we are using our excessive mobile phone radiation effect is really increased our stress, fatigue, and frustration in normal daily activity. And some days our children are also using the YouTubes and lots of networking sites, and basically this is increasing our overload of on mental workload. And basically this is called that over cognitive load. And someone you may question about the what is the cognition, or so basically cognition is the human brain is controls all the activities related to our psychology and brain psychology and brain physiology. This is the main activities which is called the cognitive load. So the cognition is basically our skill, our thinking skill, or our reading skill, learning skill, remembering skill, paying attention skill. So when this load cognition become hampers and become frustrated, become get fatigued from the overloaded activities. So if we find out the cognition levels or cognitive levels, we can help our mankind on people on that. So for that reason, I choose that topics for my PhD. So basically, the first cognitive model was introduced by Aristotle in back to 15th century. Then lot of works have been done, but uh, after that there are also very scope on that projects. So cognitive load theory was first introduced by John Sweller in 17th century, and he told about that when our working memory is really hold very small amount of information at one time, so we should always avoid overloading that to maximize our learning. So in Kuwait, we have the lab, so where we can identify and measure the cognitive loads through two module like EEG, electroencephalography machine, and also we had the functional near infrared spectroscopy machine FNIRs, which called FNIRs, and these two modules and really portable, small, but really carry a lots of fruitful information. So by these two machines, we acquisite the data, and we also took helps different types of data set from natures and University of Ukraine. And with these data sets and also the data which we got from the lab, and we processed, and we also used machine learning algorithms like SVM, LDA. We also used machine learning algorithms like ANN and CNN for these activities, and we actually classified the data, and we found out that our frontal area of our brain and our motor area, that the mid level of our brain really activates when we really think about that. But when we do multitask, our brain really got very really brain stopped working through frontal area and mid of brain. And we also found out that the person who are uh, very much used to their words, they they are used to do multitasking every day, they really feel little stress. That's the person who are new to the work like multitasking. They really feel stress more than the person who are very much experts on that works. And we also introduce some topo plots of our brain, and with that topology, we can easily describe the activation part, which part is working more on that any type of activities like reading, writing, and any type of thinking activities. And we also developed one topographic model of brain mapping model on the neurofunctional pattern, proposed neurofunctional pattern, and this model shows that the any type of activity where uh, any type of activity from by time, how our brain activates from the 0 second to the time that we work for. And we classified our cognitive load level like low level, mid level, and high level into 3 levels, and classified the area datas and the cognitive load levels with the machine learning algorithms also. And that's how we concluded our works, and I have published two Q1 journal and one Q2 journal on the perspective. And there are lots of scope on that area, and in today's world, the biomedical engineering is really performing well, and there are a lot of scopes like combining, bridging the engineering sectors and also the medical sectors, which can combine the biomedical engineers in the future worlds. And now in countries like Australia and USA are giving lots of funds for the biomedical students for accomplishing their MSc and PhD. And that's why I choose to shift my focus from Tripoli to BME. Basically, Tripoli and BME are in particularly the basic and fundamental areas are quite same. Around 60% of our Tripoli syllabus are quite similar to the biomedical field. But in that case, I have to study more about some human physiology and human anatomy, and as well as transport fundamental activity from our body, which basically shows the reflecting side of the engineering perspective. And now I think that we should the Tripoli students can also their show the focus and can get more enjoy, they can get very much enjoyment, and then can show their research reflections on the biomedical fields. And I think for doing the any type of higher studies, we should always work and reflect it to increase the publication quality, and we should always think that we should always publish and participate in good type of conferences which arranged by IEEE, and we can also show the interest in publishing high ranked journal like Q1, Q2, and impact factors, Focus Index, SCI Index journal, which will basically show, it reflect our research affinity. Thank you, sir.
Thank you very much. I believe the students got some good guidance that the current research trend in biomedical engineering, how or what are the topics in biomedical engineering you can do research, and you should also focus on publishing good quality conference and journal papers that will help you to get admission in better universities, and also not only outside universities, you can think of doing your PhD in universities in Bangladesh as well. So several universities have biomedical engineering programs. So like JAST, QUET, or in MIST, we also have biomedical engineering. So you might start with your electrical engineering knowledge to those who are in biomedical. Definitely, they might get advantage in starting research in biomedical, but it is not limited to only biomedical engineers. Those who are in electrical or even in mechanical, they might also do their research, and in future they might migrate to biomedical engineering as well, considering the more scholarship opportunities in biomedical engineering. So thanks for the guidance. So we already at 10 p.m. So we are about to finish, but before finishing, I am expecting some final words from Dr. Mehdi and Dr. Farzana. So what are your final words for our current students? Like we are organizing the event from IEEE Young Professionals Bangladesh with collaboration with Just Student Branch. So should they involve in IEEE activities, do networking, getting updated information from updated research information or updated scholarship information through this networking with young professionals or IEEE student branches, and what are the skills they should gather, or what are the areas like publications and other areas they should focus for their bright future? Any final guidance? Dr.
Thank
Mehdi
you,
first,
sir.
then Dr. Farzana.
Thank you, sir. At first, I would like to tell my students and also all other students in this platform that whatever you do and in whichever field you do your research from here on, I think 90% and more than 90% in our field based on programming. You need to know any one programming. Python is the very basic one. I mean, whatever field, even the biomedical engineering, even deep learning, machine learning, electrical engineering, in our field, most of the cases, most of the engineering fields, you need to know programming, any basic programming. Some of the cases you need to know the very low level programmings like C, C sharp, but most of the cases you need to know at least a good top level programming like Python or MATLAB. So that's a must. You must have enough knowledge, enough experience handling programming, handling codings, debugging codings, and reading and debugging codes from GitHub repositories, which contains lots of files and lots of folders. You need to figure out how to go through them and how to debug them, how to reproduce them. That's one. For second, yes, as Sir said that for creating a communicating with the greater community. Yes, you must have this in today's world. You must have a good and greater community, research community, from where you can learn new things. You can learn the new trends in your research field, and you must attend one or two conferences in your undergrad, at least one conferences to meet with young researchers, to be yourself known how the research environment, how the research community communicate with each other. So these are the experience you must have to make yourself better in research and other things. Thanks, sir.
Thank you, Dr. Farzana.
Thank you, sir, for giving me the floor again. Actually, I think for our students, we have a lot of things to tell, and we always share our views in our classes also. Basically, from third year, from my side, there is as for like Dr. Mehdi, my advice is also kind of similar, that we should always for IEEE as a volunteer or a participant or of IEEE, I also think that one programming language is basic for our students, like Python, MATLAB, whatever, because I heard from my one brother who is pursuing his MBA in Australia, and that in that place the programming language is also compulsory for his also an MBA student. The programming Python is like compulsory for him. So for an student of commerce, uh, he had to learn the Python also. So one programming language is very basic, and from third year we had completed know that around 60% of our syllabus, and we also know the basic terms. So the students who are really eager to know about his research, he or she should focus on the part that which part he want to do his higher studies. So in that case, if you want to go towards the hardware process, he should also learn about the simulation software like circuit design or logic design process. So then he should also had to he can also uh, really learn about some conference papers in every week or every month. One conference paper he can, if he learn, he can also know how to write a paper. In what manner he can gather his knowledge in one page. So then he can also share really in today's world, he can get all type of resources of how he can publish a good journal or a conference papers, good conference paper, and how he can engage all his research knowledge in one umbrella. So I think our students can also can take help from any significant field from related to his professor, which professor is expert on that his required field. He can also take help from the professors also. And I think today our teachers is very much helpful, and they also tries to share their views and knowledge about the research of their expertise on the required or interesting research field of today's world. And I think our students can always uh, feel free and unhesitedly, and they can go any not only just they can take help by messaging or texting or by mail any type of uh, research knowledge from anywhere of the world. I think most of the professor always responses, and they can go through any of that interested research fields. Thank you.
Thank you for the final guidance. So we already heard from our two panel members. So I believe it will help our students to pursue their higher studies at home and abroad. And I believe they will be motivated enough to uh, make their career more research oriented, as well as they will help you to get better position even in academia and industry as well. Because in outer world, having a PhD will definitely help you to get a better position in industry as well. Because the culture might not be that much practiced in Bangladesh, that after having a PhD you will get better position in industry, but this culture is followed abroad. So whether you want to settle abroad, so a PhD or a higher degree will definitely help you to get a better position there. So without further delay, because it's already 10 past 12, so I'd like to thank our both panelists for sharing your nice experience, nice guidance, and motivating our young professionals as well as final year students or young students. So thank you, and I'd like to request the host to share some token of memento like certificates if you prepared for the speakers.
Thank you.
So I'd like to request Dr. Mehdi Hassan to receive this small token of appreciation from IEEE Young Professionals as well as IEEE Just Student Branch.
Thank you, sir, and thank you also the International Young Professionals Bangladesh and also IEEE Just Student Branch. Thank you.
Thank you. Then for Dr. Farzana. So Dr. Farzana Khanum, please accept this small token of memento from IEEE Young Professionals as well as IEEE Just Student Branch. Thank you for your time.
Thank you. Now, I'd like to ask Dr. Mehdi Hassan sir to present the certificate of appreciation to the moderator.
Thank you, sir, to moderate, to be the moderator of this wonderful session. Thank you.
Thank you. I am really honored to be with Just Student Branch for your nice arrangement for the good speaker from abroad as well as a good speaker from inside universities to share their experience. Thank you, Just Student Branch, for your nice organization.
Thank you, everyone,
So
to
we
make
might move to the conclusion.
successful. I think we can officially close the session.
Ratul, we have quiz session.
Oh.
Okay, so we are waiting for the most exciting part. Actually, we have a quiz section after every session. Usually, we have it after the keynote or the technical talk before the panel discussion. But today we had the panel discussion just after the technical talk. We might start the keynote. We might start the quiz session. We have 29 participants here, and hoping it will be an interesting one. So all the members joined here, we might participate. So would you please share the or start the quiz session?
Assalamu alaikum. Thank you, Anand sir, for giving me the floor. And thank you, Fahim Bhaiya, for I am sharing the quiz link, sir. Hello everyone, I already shared a link in the chat box. Can you join today's quiz? If you have any problem to join the quiz using link, you may use the game pin code. The game pin code is 792127, or you can scan the QR code. In the meantime, I would like to share some basic rules for your convenience. You will face 10 questions in this quiz session. For each question, you will get 4 options. And to answer it, you will get just 20 seconds. So be hurry to choose the best answer. And it's almost 10:15 p.m. So I'd like to request all the members to join fast into this quiz session. Hello. I believe I am audible to everyone, right?
Yes, you're audible.
Thank you so much. Okay. Please, we will start our quiz within 2 minutes. Please join fast. As it's dinner time to everyone, so we need to hurry next person. Kindly join fast. We will start our quiz 10:17. Please join fast. Only 13 participants I can see. At least we can expect 20 members. Okay. I'll start previous quiz. What is the very first step when starting a new chip design? The options are writing the specification, writing the Verilog code, making the floor plan, and running the simulation. What is the very first step when starting a new chip design? Last 5 seconds. Try to answer first. Now we are moving. John Bhai is on the top. Next question. What language do engineers use to describe how a chip should work? The options are Verilog, GDSIS, C++, Python. Try to answer first. Only. Okay, that is our next question. What process turn the written code into logic gate? The options are computation, verification, floor planning, logic synthesis. Process turn the written code into logic gate. Verification, floor planning, logic synthesis, and computation. How do you check if your code works before building the chip? The options are synthesis, emulation, place and route, and simulation. How do you check if your code works before building the chip? Option A, synthesis. Option B, emulation. Option C, place and route. And option D, simulation. Question. What is the main job of place and route? The options are arranging and wiring gate, checking the time, creating the logic gate, and writing test bench. What is the main job of place and route? Arranging and wiring gate. Option A. Option B, checking the timing. Option C, creating the logic gate. Option D, creating a test bench. Okay. Next question. What check proof the chip will run fast enough? The options are power analysis, static time analysis, design rule check, and functional simulation. What check proof the chip will run fast enough? Power analysis, option A, option B, static time analysis, option C, design rule check, option D, functional simulation. Okay, Shweta Bhai is in the top. Next question. What check makes sure the layout matches the factory rules? The options are DRC, option B, LVS, option C, STA, and option D, formal verification. The layout matches the factory rule. Option A, DRC, option B, LVS, option C, STA, and option D, formal verification. Okay, next question. The Shahir Bhai is on the top. What do you call sending the final design file to the factory? The options are GDSIA, sign off, silicon, build up, and tap out. What do you call sending the final design file to the factory? The options are GDSIA, option D, sign off, option C, silicon, build up, and option D, tap out. Okay, next question, no change in the top. The final step before tap out, ensuring all check pass is called. The options are final verification, regression, bring up, and sign off. Before tap out, ensuring all check pass is called final verification, regression, bring up, sign off. Okay. No change in the top. Last question of today's quiz. What do you test the first real chip that come back from the factory? Option A, on an ATE, in a simulation, on an FPGA, and in an emulator. First real chip that come back from the factory. ATE, simulation, FPGA, and emulator. The options are. Okay. Let's see today's question. MD Shoizuchan Bhai is in the third position. Mushfiq Bhai is in the second position. Shahryar Bhai is in the first position. Thank you so much for cooperation. Back to the host.
Thank you, everyone. Thank you for making this session successful. I think we can close the session now.
Take a photo.
Oh, sir, sorry. Now, if you can, please open your cameras. We would like to take a final photo.
Someone take a photo, please, and let me know if it's done.
Mushfiq Shoizujaman, any update? Okay. Thank you, everyone.
Thank you, everyone who joined today. And I think, Abdul, you can close this session today.